Yeah.
I removed the marketing, Tom.
Sorry.
Hey everyone, we have an Intel GPU here. It's real. There's actually one running right now. It is running F1 2021, and we're going to be benchmarking an A380. I'm joined by Tom Petersen today, formerly from NVIDIA. We've done a few videos together.
We have done quite a few.
And Tom is on the very technical side of things. So we're going to be talking about some of the functionality of the card's architecture a little bit, clock and voltage behavior.
Yeah, absolutely, clock and power and all that.
This is going to be a pretty technical video, but we are going to be starting with some discussion about the new Intel A380. And can we name this one, Tom? Do you want to?
Yes, it is. Well, let's see. Hold on. You want to come here? Can you come here? It is the Arc A750 limited edition. And we're going to talk a little bit about that as well.
Before that, this video is brought to you by Be Quiet and the Silent Base 802 case. The Silent Base 802 got high accolades in our review for its high build quality and its versatility in both silence-focused and airflow-focused builds. The 802 comes with swappable mesh panels or noise-damped panels, so you have options for either approach. The Silent Base 802 case is able to fit larger builds as well without being overbearing, and it stands out for its mechanics quality and assembly quality. Learn more about Be Quiet's new case at the link in the description below. Okay, so first of all, this card is not the one we're going to be reviewing immediately. We will be working on it, but this one they brought because you guys had this at IEM.
We did, we showed it there.
So it's the same model of card that was at IEM. I think it's gotten maybe one cosmetic change.
It has had a little, but this is the first time we've shown it actually doing anything cool.
Yes, I may have made snide comments about the fact that it was encased in glass and not plugged into anything.
You may have.
Intel displayed the definitely real, functional, and usable Arc GPU. The unit in question was imprisoned, eternally rotating in this acrylic case. We think this probably is symbolic for Intel's ability to hit its release targets. And I apologize. So it does actually work. Let's start with, I guess, quick flyover of the A750. We'll come back to the A380. This is the one that it's already out. It launched in
available.
China.
You know, we've not given anybody a lot of details about this yet, so we wanted to come and give you extra detail about what that's all about. But let's talk about what, like, hey, what's really going on overall, right? So I have just a few slides. You can see right here, you know, Intel Arc Graphics is going to have 3 bands. There's a 7 series, there's a 5 series, and a 3 series. And all the products are going to be like A3 something, A5 something, A7. So the A is like our first letter. It's going to be Alchemist is our code name. A is the product name. When we go to our next generation, which by the way are already in development, our Bs are going to be, you know, a Battle Mage is the code name, and B whatever. So you'll know exactly, you know, which performance level you're going to
get. And so in terms of nomenclature, when we were talking about this video beforehand, we want to do a bunch of technical stuff, but I was talking to Tom about Intel's new to DGPUs, and I'm not 100% sure I have all the names straight yet, so it's probably good to get everyone on the same page. So, I mean, to me, 357 is easy enough. It's just like the I series naming for CPUs. So for code names that we need to be aware of, Alchemist is the current version, so
current
A380.
chip.
And Battle Mage, is that next?
That's our next architecture, and after Battle Mage, which we're also already working on, is Celestial.
So is it alphabetical?
It is alphabetical, and the one after that will be, I don't know if we talked about the one. Have we talked about that?
Yeah, Druid.
All right, Druid is the one after that. Right, ladies and gentlemen, put your hands together. Yeah, once you kind of understand our positions, you can actually see how do you embody those products, right? So we've got 3 different segments. Well, to fill those 3 different segments, we built 2 chips. There's an ACM G10, which is, again, Alchemist G10, and that is our large die. It's got 32 Xe cores, and I'll tell you a little bit more about what an Xe core is later.
And I want to relate this back to NVIDIA briefly. You don't work there anymore.
I don't.
But just because it helps me kind of keep everything straight. So for G10, G11, are we talking about basically the die naming itself?
Yeah.
What will appear on the die, in other words?
So
for like NVIDIA, you might see like a GA102-300 or something like that. So that's kind of what these are. It's where, I guess making sure everyone's clear, it's video card name or product level name versus GPU itself.
Exactly. It gets confusing, but there's an architecture, which is like Battle Mage, Alchemist, and then there's segments, which are those A7, A6, and then there's chips that are sort of like inside ball. How do we make those products?
Right. And then the product itself. So
yeah,
A380
and we
or
use the
whatever.
same names for all the different sections. So
Yeah.
there's something called an XE core, which we'll talk about later, and there's 32 of them on the G10 and 8 of them on the G11.
So
basically a big die, a little die.
Right. So for these, what are these found in the G10, G11? What in terms of product stack?
So G10 is going to be in the 5 and the 7, and G11 is the 3.
Okay, got it.
So we made those backwards.
Yes, but that's what
That's what everybody else
other
does.
other companies do as well.
Exactly.
Okay, so XE cores, definitely want to talk about that. For relating it back to stuff everyone's familiar with, you'll see listings with NVIDIA, it might be SMs and CUDA cores. With AMD, you're talking about compute units or CUs and stream processors, they call it.
Exactly.
So if we were to relate, Tom, I don't know if you've heard this, but bigger numbers are better. And NVIDIA's number, when it's cores, is like 10,000.
Yes.
Therefore,
better.
Right.
Tens thousands of times better.
Yes. So how does this relate back?
So they don't really relate back.
Yeah.
There's no easy way to do a conversion because it's all about microarchitecture. But when we talk about our XE cores in more detail, you'll see how wide they are and how many they are, and that's really a better way to understand
When
it.
you talk about core width,
can
you give me some examples?
So I can talk about our core width is going to be roughly 256 bits wide, and we're going to have a vector unit, and we're going to have a matrix unit, and the matrix unit is actually built for doing AI. It's much more complex, but we'll talk through that.
So is the bit width, the maximum bit width determined at sort of an architectural level, and then it gets, I don't know if they're typically fused off or just downbinned below that, or is that a constant width?
It's a constant width. So the way to think about it is when you do a graphics architecture, you have sort of like a width of SIMD, and that's saying how many parallel data operations are associated with each instruction.
Right.
And ours is going to be 256-bit wide, which is basically 832s in parallel with 32s. So that's it.
Okay, excellent.
Now we do depth and compute units differently. So if you look at an XE core, there are sort of like different numbers of XE cores in different chips, and that's how you get wider.
Right. So L2 cache you have listed, 16 megabytes, 4 megabytes. Is there anything on here you feel like deserves some additional attention?
I always like to call out details so nobody's surprised. So you'll see on here we have a by 8 PCIe Gen 4 on the G11, and there's a by 16 on the G10. So that means that you're not going to use all of the PCI lanes for the lower end because it doesn't need it given the performance level.
Right. So for anything with a by 8, I guess we were talking about before how don't be surprised. In other words, if part of the PCIe footer is like
may not be populated.
Right, the pins might all be there, but you might be missing some traces off to the side of it, and that is happening at
the chip
GPU
level.
die level.
Exactly.
Yeah,
exactly.
Okay.
So if the chip doesn't support but 8 Gen 4, that's plenty of bandwidth for a chip at that sort of performance level. But a lot of times the cards will still put all the copper down there to kind of make it look as the gold fins, but some may not.
Yeah, and even if it's there, it's not adding.
It's not doing anything.
It doesn't add more lanes.
It's not doing anything, yeah.
So for that, is this type of decision, I'm just curious about, when internally when you're designing by 16 by 8 or something, is that sort of I guess what drives the decision of
it's all cost performance.
Right.
So when you're for the G11 die, that's at our entry level cost and an entry level performance, and especially when you're doing Gen 4, there's just not a lot of sensitivity to wider than by 8.
Sure.
So it's sort of like not useful and it's expensive.
Right.
So we can make the die smaller and more cost effective. Each one of these PCIe interface pins are actually pretty big. There's a PHY, and by removing those, we can actually make the die smaller. The ring is smaller.
Got it. Okay.
And it's basically just a cost performance.
So if you look at a block diagram of even a CPU or something, you'll see blocked out, like on a CPU, you'll have PCIe lanes, you'll have USB I/O.
We might be able to get you an image.
Yeah, if something like that's available, great.
Well,
but yes,
look at it.
Basically just removing part of the die so that you can shrink it, or you can fit something more important.
Exactly.
I see. Yeah. Okay. Cool. What's next?
Well, then of course we're going to talk a little bit about A380. So the A380 card that you have there is basically one of our entry-level discrete graphics cards.
And this is a board partner model.
That's Ganeer. And it's basically our first retail available product with the A380. We're very excited about it. It's got 8 XE cores, and it's got a graphics clock of 2 gigahertz.
Right, and I do want to get into that. First question though is, when this launched in China first, it was basically only available on pre-builts, right? Like SIs. We ordered one, and I think the pricing for those was like $500 to $700 fully built. Somewhere along the way, that was conflated with the actual cost of the video card.
Yes.
I don't know.
Well, let me just I'd like to clarify things.
Yes.
Right? So we have a Chinese price that's in RMB.
Right.
There's going to be a US retail price if this becomes available in the channel here.
Right.
That's going to range between $129 to $139 in the US MSRP suggested.
Yeah, so not only is it not the price of the pre-built itself, it is also, I think the RMB price
it's like 1,030, something like that.
So it's like 150 USD.
Yeah, and that conversion has a lot of complexity to it, so we thought we'd just make it clear what we expect the US MSRP suggested
You
price.
said like 130, 140 on this?
I said 129 to 130. Oh, 129 to 130.
Yeah,
130,
140.
Yeah.
I removed the marketing, Tom.
Sorry.
The marketing is $1 here.
Yeah, I got it.
I removed the 1 penny. Okay, so for clock rate, 2,000 megahertz. If I'm reviewing an AMD or an NVIDIA product, I know what that means because I have baseline performance. As everyone, I think, in this room knows at least, AMD, NVIDIA, for example, the clocks, you can't just do an equal symbol between them or greater than, less than. There's a lot more to it than that. Even if you get out of the sort of core and frequency itself and you get into stuff like memory, memory bandwidth, anything like that, memory capacity, it can mean a different thing. So 2,000 megahertz to me with Arc actually means nothing right now.
Absolutely.
So can you?
I can help.
Okay.
I can help. Okay, so first of all, I think, unfortunately, I did a briefing for mobile, and I think people got confused about what I actually said. So I'm going to say it again more clearly with your help.
Sure.
Okay? So here we go. GPUs, all GPUs, have internally this concept of there's frequency and voltage, and there's a trade-off, and you've got this little line that kind of represents what operating point is available. Right now, depending on the load, if it's a light load, the GPU will tend to run a little higher on that curve, and if it's a heavy load, it'll run lower. That's why there's not one clock number, right? There's lots of different clocks depending on what voltage you're running at and what your workload is, okay?
And there's scale based on power consumption typically as well.
So if you have different power levels, but at the end of the day, there's like this distribution, and so it's hard to describe what the performance is when there's a distribution. So what we've said is we're going to draw our line right in the middle.
Okay.
Right. So it says if you look at like TimeSpy as an example, or maybe pick 2 or 3 titles that are typical, we'll see a distribution of clocks on that curve, and we're going to draw a line right in the middle, which is sort of the average or the median clock, and that's our spec.
And so to make a few things clear then, it's not like the old days with GPU clocks where there's a clock, and that's what it does.
Yes.
And I think we've talked about this a lot before, but actually talked about it with you previously at a different company. What parameters are you looking at? So
there's lots.
There's power.
There's power. There's temperature. There's utilization. There's even looking at different units trying to decide. And because we're Intel, we can actually cooperate with the CPU. So think of it as in a mobile design, what clock you're running is kind of heavily influenced by what's happening on the CPU and the GPU. But on a discrete part like this, where we're not really connecting at that level, it's mostly temperature, power, and utilization. It's going to kind of drive you up and down the curve.
I guess relating this to something like GPU Boost, for example, like the technology, are you doing a similarly branded type of thing? Is there anything you're talking about?
We don't have a brand for the way the clock works. And the technology is different, the way our algorithm works, but the concept at a high level is very similar, right? There's a dynamic clock, and you're going to have to pick an operating point, and you're doing it based on a bunch of real-time telemetry. There's a lot of creativity and a lot of ways to do this. Some are good and some are bad. I think we're doing it a good way, and it's going to get better. We may end up giving it a name just because people want to know this is like graphics clock controller Rev 1, and then there'll be a Rev 2 and a Rev 3, but we just don't have a name yet. Just to make it clear, the clocks vary based on your power budget. So like on this card, it might have one power level, which I think is typically around 75 watts. But you might have another card that would be like 90 watts. So you can think of it as with our design and with others, if you add power to your budget, we're going to tend to run higher clocks. And since we're already running Boost, what we're going to call our graphics clock is already running at 2 gigahertz on this SKU. I mean, it's going to be sustaining clocks far above that.
Is the plan on the power side, is the plan to allow, I guess 2-part question. One is, will board partners have the flexibility to change vBIOS to have a higher power target?
Yes, absolutely.
And then second part of the question is, will users?
Yes, absolutely.
Okay. So you knew where I was going already.
Yes,
I
absolutely.
saw you already jump into the next
no,
question.
I don't jump, but I get ready.
Yeah.
Get ready.
User or board partner vBIOS control. I'm assuming, I mean, I don't think this would really function any differently on Intel than anyone else, where you basically have, if it's at a user level, there's a slider, and you get plus 15% or whatever.
Yep.
And then you're adjusting the power budget available to the GPU to boost higher or to pull more voltage.
Yeah, we'll talk a little bit about, I don't know if I'm going to give you an
Sure.
overclocking slide here, but just similar to other people, there's two knobs right now, or
Right.
actually a couple more than that, but the big ones are, hey, I'm allowing more power up to the limits that the manufacturer set,
Okay.
and that's a slider that we make available to users.
Right.
Of course, the card's going to get a little louder if
And
you add
hotter
power.
for the
and
VRM,
hotter,
yeah.
right? The other slider is I'd like to increase performance.
Right.
Now, when you slide that performance slider, it's not going to necessarily add power. It's going to raise the clock at every voltage, and that will have the effect of reducing margin, but you'll get higher performance. Right. So if you reduce margin, you might have some games that start to crash. You might, you're kind of running it in an area. But the power slider doesn't do that. The power slider just says, I'm willing to have more power, run it in a safe place, and all good.
Cool. What do you have next on the
Well,
slides?
I think after that we could talk about performance.
Okay, sure. So I'm going to jump in here because this is now Intel's.
This is bull.
This is Intel's performance. We have A380s, so we bought the one pre-built system that's arriving within days at this point. That has, I think, the same model. A380.
It should be the same.
And then there's these that one of these might get left here, it sounds like. So we're going to be doing our own testing for A380s, which I guess is what this is. And obviously, you all can check back for third-party testing, but I'm happy to allow you to.
No. I will defer to your expertise,
Sure.
but I will say that my takeaway is this is our entry into the discrete gaming market,
Right.
and it's a very important moment for us. And I want to thank all the engineers that have been working night and day on the software side and the hardware side to get this performance level. Given the chasm that we've crossed, I'm just excited to be here.
Yeah, so, and I think it's probably worth talking about drivers a little bit too, about how that, in terms of challenges, with Intel coming to market, it's great that there's going to be a third competitor and sort of put some pricing pressure on NVIDIA and AMD, where it's crept up a little bit too much, in my opinion, not to make it too easy for you, but I don't think anyone disagrees. So it's crept up a lot. Having competition there is good. At the same time, when Intel launches, I mean, you are going to have to be doing a lot of driver tweaks and improvements and optimizations.
Absolutely.
And I think that's just going to be...
This is a lifelong endeavor for Intel, right? Because our driver is very complicated. It's been evolving over 20 years, right? We are the largest graphics manufacturer in the world with integrated. But the truth is, our driver has really not been focused on gaming until just recently. So we have lots of games that are older that we haven't optimized for. So we have a lot of work to do there. But on newer titles, DX12 titles, Vulkan titles, and even other games that are really optimized for Intel, we are going to kick ass. So, I mean, maybe not kick ass, but I don't mean that in an aggressive, assertive way. I mean it more like in a humble way.
Sure. Yes, we are going to humbly kick ass.
In like the area where the software and the hardware come together, it's a great engine, right?
So how do you make the decisions for building the driver? It's not reasonable to say we're going to optimize for everything because there's infinity games.
Yes.
So, I mean, I guess if we break it down into newer titles and older titles, where newer is maybe within the last few years forward.
Yeah. You can almost go API.
Sure. Okay.
Right? So
sure.
if it's like certain games on newer APIs run like as designed, like as I would want to see it. If I opened up a little pipeline view, it would look just beautiful.
Right.
Those games are going to be great on Intel. The other games that are running on DX12 or Vulkan, they're going to be really good right out of the get-go because we are sort of optimized for that newer API.
Right.
And it's the older games that are like DX9, DX11, where we're going to be a long job of it constantly improving those. But we're not going to be stupid and think that people aren't going to notice that. There's going to be lots of people that see that.
Well, and so you're doing work up front too. So for the initial rollout, how are you determining, how is Intel determining, these are the older games we want to work on? Because like I said, there's too many. You can't just tell the driver team, like, I don't know, pick some.
No. We have a very rigorous way of picking titles. We use Steam data, and we also look at games you use, and we look at games that other reviewers use. And we try to say, hey, right now, what are our top 100 titles? And they're all going to be looking pretty good.
Sure.
But right away, I already know that, well, some of my favorite titles are not in that list. So I'm going to be wishing that we had picked my titles. But it's going to grow over time.
Yeah.
And I expect that as reviewers start running it, there's going to be different games that I haven't seen, but we're going to work through it.
Was architecture next?
Yeah, we could do architecture if you want. Just a deeper dive, or we could do that as a separate, whatever
Let's
you want
do architecture, yeah.
Okay, so this is for all XeHPG, and I'm just going to roll through it so you can get a sense of what we're talking about. We basically have the Xe cores, which is the compute. There's the media engine, which is doing things like AV1, it's doing other hardware accelerated decoders. There's a great display engine, which is usually 4 heads running at 4K and maybe even 8K at 60 hertz. And then we have fixed function hardware for the graphics.
4 heads running at 4K is 4 displays. Is that
I'm
correct?
sorry, yes, heads is a display, and heads and displays are slightly different, but they're close enough to heads, displays, yeah. So
proving the point of clarification.
Sorry, thank you, yes. This is the render slice, and this is what most people would think of like an SM. A render slice is made up of some amount of Xe cores, which is our compute unit, and then it's backed up by hardware ray tracing units, and then fixed function logic for things like samplers and pixel backend, that kind of stuff.
So for labeling here, XVE, is that vector?
It is.
XMX?
It's a vector engine, and XMX is the matrix engine. Yeah.
And load store is standardized nomenclature. Is that cache down
there's
a cache at the bottom?
Yep.
Thread sorting unit.
Thread sorting is pretty cool.
So let's talk about that a little bit then.
Okay, so whenever you're doing a wide SIMD engine, which is what this is, the order of threads that you apply into your logic matters, because if you have one thread that takes a long time and it has a lot of work, it'll gate the reuse of all the other lanes effectively.
I see.
Right?
Yeah.
So you kind of want to put threads that have roughly the same length to execute at the same time. And that's what thread sorting does. In this case, mostly that thread sorting is operating on the ray tracing unit.
Okay.
So ray tracing, we'll talk a little bit more probably as a separate thing.
Sure.
But we have some great hardware ray tracing units.
So there are hardware ray tracing units in here, which I think we knew about publicly already.
I think you did.
Yeah. For the next part, I see sampler geometry something.
Rasterizer, pixel backend, high Z.
High Z, what is high Z?
High Z is basically acceleration for Z buffer calculation.
Okay.
So think of it as whenever you're rendering, you need to know how deep things are into the frame, and that's used for things like color, but it's also used for occlusion detection.
Yeah, and isotropic filtering.
Yeah,
I guess,
all that kind of stuff.
Well, yeah.
And this isn't, you can do early culling with that kind of acceleration. When I think about what is a Z calculation, you're kind of trying to say, where does this triangle appear relative to other triangles so that I can throw it out early. And so think of it as you keep a record of what was the closest triangle you've seen.
Oh yeah, we should actually, just really briefly, so for what we're actually talking about, you're talking about like geometry that is technically within the view frustum of the player.
Exactly.
But is occluded by other geometry, and so you don't need it. So he's talking about filtering it down.
Yeah, you want to get rid of that stuff, right? And so if you can build some simple dedicated hardware that will allow you to figure out when you don't need particular triangles, that lowers the work in the rest of the pipeline.
Right.
And so we have some dedicated hardware that's making that calculation quick.
Okay, cool.
Well, before I say this is just the building block, we scale it at obviously putting multiple slices together. The Xe core is the guts of the compute. So we have Xe, the vector unit, and the matrix unit, a load store.
Right.
When you dive into it, though, it kind of gets pretty cool, because looking at the vector units, it's 16 256-bit wide units. I already talked about that.
Right.
It's 16 matrix engines, and I have a picture to describe it. I don't know if you want to do this.
Yes.
All right.
Let's do it.
So when you're doing graphics, you're usually running what's called a shader program. And this is a standardized language that communicates what operations do I want to do per pixel to make the color correct.
Right.
So that's normally done multiple pixels in parallel. So that's what the vector is, right? It's a single instruction that's sort of like the program per pixel, and then the units are set up to do 8 pixels at a time, basically.
Okay.
Right? So a Mac is a multiply accumulate, and in our engine, we can do 16 multiply accumulates per clock. That's 1 multiply, 1 add.
Okay.
Okay? And if you think about DP4A, it's a way for us to chop up that math into smaller blocks. So instead of doing 32 bits at a time, we can actually do 64 ops per clock.
Okay.
Which is just a way to break it up so you can get more parallel calculations. And the last step in that craziness is what we do in our matrix
Right,
unit.
yes.
Yeah.
Now it's 3D chess.
Now it's 3D chess,
Yeah.
and we're actually taking two matrices of numbers and doing a multiply accumulate all at the same time.
Right.
And that's just a graphic that says, you know, we're using a systolic array, and it does up to 16 times the compute versus.
And systolic, we were talking earlier. I said I only know that word from blood pressure.
And I said that's exactly right.
Yes. So it's pressure, I guess, in that sense.
The way to think of it is
pump.
like it's pumping, right? It's pumping, and the way to think about it is the accumulate is what's the pumping through the structure,
Right.
And at each level you're multiplying and adding another set of operands, and then pumping it down to the next layer.
And then this, if we talk about it further, would be a separate video.
Yes,
But that kind of starts getting into some AI stuff as well. Right?
AI and XESS and all that good stuff. Yeah.
Which feeds not just AI like, I don't know, like you're running a factory AI, but AI as in, like you said, XESS or something.
Graphics AI, taking low quality graphics, turning them into high quality graphics using AI. It's really cool, but you're right, it's a different video.
Yes.
Maybe I'll come back. Who knows?
Yes.
Yeah. And I think, my friend, that's all the rest is just fixed function stuff.
Cool. So I guess main takeaways right now are on the product level, the A380 is kind of finding its way into the market. And then the A750 you've shown running, it's been running F1 now for quite a while. I always have to ask this, but timelines on things, so.
Sooner than you think.
Okay.
Yeah, so you know we could keep working. It's like you got to at some point. You know what? We just need to start getting feedback.
Right.
And to do that,
especially for drivers.
Especially for drivers, and we need to just get into the market and get that feedback and start the process.
Right. One card for the A750. There's an A380 that may or may not end up widely spread in the U.S. market.
Yeah, it's kind of up to our partners about how A380 goes.
Right. And then is that the only names we have right now?
Ryan, do we have more names we can talk about? Yeah, we cannot talk about more names.
Okay, yes.
It's up to our partners to disclose what they want to do.
Right. Inventing names is, I know it's hard work, and I know a lot of letters and numbers go into them, so I wouldn't expect you to just share them to anybody.
Terrible, yeah.
Right. Well, Tom, thank you for helping explain everything. I'm sorry to hear you're only going to be able to have 26 generations of these with the alphabet dictating the naming.
We're going to have to, every couple of 10 years or so, NVIDIA goes through it, AMD goes through it. We're going to go through it after 26 years.
Yeah. You have to start doing the Microsoft Excel like AA380, AB380.
Don't.
It's okay. It's far enough in the future.
It's way off.
It's not a problem for either of us.
Way off. Do we have an E name? Do we have an E code name? I don't think we do. Maybe your reviewers could help us.
There you go. Leave your this is dangerous. Leave your suggestion
for the E code name.
For something starting with the letter E in the comments below. Anything, as long as it starts with a non-silent E.
But it's also a character. Yeah.
Yeah, ideally a character. Maybe you choose something from one of the D&D players' handbooks so I can scrutinize Intel's naming choices again. All right, we're going to have another video. Thank you, Tom.
Great to see you.
And we'll see you in the next one.